All right, so today's challenge, day 6 from Advent of Code. What the puzzle is for part 1 is that we get a map, a really huge map, and we have a bunch of hashtags, and somewhere we have an arrow pointing in some direction. So what it says here is that, okay, the arrow is a guard, and it can be pointing in any direction, up, left, down, or right. And the up one will be the up arrow, left arrow, right arrow, and down will be a V. So based on what we find, we have to move the guard because it will be patrolling the area. And how will it be doing this? It will be doing it with 2 strict rules. It will always walk forward, and then when it hits an obstacle, like a hashtag, then it will turn right 90 degrees. And that's what it always does. So if it begins here, then it will go up to this one, and then it will turn right. So we can see the little step-by-steps that it shows us. It arrived here, it's going to turn right now, and then it's going to hit this one. So that's how we arrived here. Then it's going to turn right again, and it's going to go down until it hits this one, and so on and so forth, until it escapes. So here we can see that it went to the edge of the grid. So it did a bunch more steps until it finally got out. And when it escapes the grid, so to say, then the problem is well done. We don't have to move the guard anymore, but we now have to calculate, okay, how many spaces has the guard visited. So we can in this example, they mark every space that the guard visited with the X, and then eventually here we can see that it escaped from this move, and then we just have to count, okay, how many spaces has the guard even seen while it moved. And in this case there's 41 distinct ones, and we have to take the entire puzzle input and we have to calculate this. So if we do this in Python, I've taken the input and I've put it in a file, and if we just quickly find the arrow, for me it's an up arrow, for you it's going to be something different. Every input for every person that does the challenge is different. But for me, it happens, the guard happens to look up. So we open the file, and I've made a function to just read the map, and when it opens the file, and then it just returns to me a grid, because I want a grid of the sort of X and Y coordinates so that I can move like easily. So I don't have to open the file and read it every time when I want to check something. It's easy to just put it in a map grid, and then I can work from there. So what I do is I read the map, I give it to the grid, and the grid I give it to the simulate grid, which is another function that I've made. And right here we can define some directions. So we can go to the right, we can go up, we can go left, we can go down, and these are just X and Y coordinates. So first thing that we have to do is to find where the guard starts, so its starting position. So we have to iterate through the rows and the columns until we find any of these characters. So the up arrow, the right arrow, the down, or the left. And in my case, it's an up arrow. So actually, if I just remove these here, it will still work, just because I know it's an up arrow. But we have to have all of these so that it works for any type of input file. So once we find this, we create a visited positions, because we want to store them, right? So if we think a little bit in terms of where the guard has been. So if the guard starts right here and it's pointing upwards, then it's going to go here. Let's say there's a block here where it can't go. It's going to turn right. It's going to hit this. It's going to turn again. It's going to do this. It's going to do this. So there's a lot of moves that the guard is doing, right? But the thing is, we can't just count how many steps the guard has taken. So it's taken 1 step here. It's taken 2 steps here, 3, 4, let's say. We can't just count the steps and then keep doing +1, +1, +1 every time it takes a step, because if it happens to cross the same space again, then let's say over here it's step number 10 once it crosses this way, but once it crosses again, it becomes step number 24, and then we add another number here. So we count this place twice, which we don't want to do. So instead of storing the X and Y coordinates in a tuple, for example, what we can do is we can store it in a set, and the set is just basically a tuple, but it only has unique values. So then we won't get any duplicates, which is exactly what we want. So if we cross a certain XY coordinate twice, we won't be adding it twice, which is good. Let me delete this. Okay. And we have to keep checking the next position based on what the direction is now. So we keep looking for the new position. And then what we have to do is to check, okay, is it outside of the grid? Then we would stop. But if it's not outside the grid, we have to check, okay, is it blocked by a hashtag? So is there a block somewhere? Then we have to do something, we have to turn right. But if it's not blocked, we still have to do something, which is move forward, which is what we always do. We always move forward. We only turn right if we find a block. And then what I want to do is just to return the length of the visited positions. And this is the easiest way to just count how many visited positions we've done so far. So we return this, and then we get this into result, and then we print it, and we get, let's see what answer we get. I think it was a couple of thousand, yeah. So 5,000 something right here, 5,300. And did I get the same thing here? Let's see, in part 1, I got 5,318, so yeah, 5,318, great. So that was part 1, and now for part 2, it's a bit similar, but we have to do something to make the guard get stuck in a loop. So we have one block that we can add somewhere. So in this example, the O here is the block that we add. It wasn't there to begin with in the original input. So we add an obstacle, and our goal is to make the guard be stuck. So the guard starts here, it goes up until here, it goes here, it goes here, it goes here, and then it turns right again. So it gets stuck. It keeps going in the exact same loop. So what we have to check is, how do we know if the guard is stuck? How do we know if it's stuck? And we know if it's stuck if it goes in the exact same direction twice. So let's say that this is the path that it takes. So if this right here was a certain XY coordinate, then we can see it passed here once and it passed here twice. So if we see that it passes through the same place twice, then it means that, okay, it's in a loop. And another thing that we have to check is, okay, if it passes through a block, it can't pass like this and then also pass like this through the same block, because then we don't know if it's a loop or not. It has to pass in the same direction twice in the same block. That's how we know that it is in the same loop. So how do we do this? We store each position where it's visited, and we store each direction that it's been in. And one more thing, how do we even check where we could add the blocks? So if we add a block right here, for example, right? If we add our new block right here, how do we even know, okay, is it even possible for it to get stuck? So we could do this in an efficient way or non-efficient way. The non-efficient way would be to check every single place, every single XY coordinate in the grid, and to add a block somewhere, add it here, remove it if it's not stuck, add it here, check if it's stuck, try again. But actually, if we have the grid of visited places, so this is the visited places, for example, then we know that if we add a new block outside of the visited spaces, then the guard cannot get stuck, because it will never bump into these new ones that we add. So we have to add it somewhere where the guard has visited before. So what we can do is we check, okay, which places has the guard visited? Once we find all of them, we iterate through each place that the guard has visited, because these are the only places where we can make the guard take a new path. And then we add an obstacle here, we add obstacle here. So we iterate through everything. We add the obstacle everywhere, not all at once, but once in this position, we check if it's stuck, we remove it, we add another one in the next position, and so on and so forth. So there's a lot of steps to check, but to see absolutely all of them, like how many have been stuck, we have to actually put it in every position that the guard has visited. So let's see how we do that. So here we have the exact same thing. We open the file, we get a grid from the read map, and I've made simulate guard width tracking. So it's kind of similar, but we're also tracking it. And of course, we're using a set again because we want to keep the elements unique. And then we're going to use this function as well, causes loop with obstruction. But first, we're going to use find all loop positions. So how are we going to find all the loop positions? Well, we have to, let's see. We have to test only the visited positions, of course. And then we will give it the x and y, and we see if it causes a loop. So this whole function checks does a certain grid with at the x and y positions with the certain guard position and a certain guard direction. Does it cause a loop? And this just helps us because we have to check if there is a loop so many different times. So it just helps us if we make a function. So in this function, we have the sort of similar to what we have in part 1. So we have the directions again. We have to check the guard, or we have the guard position. We don't have to find it again, actually, since we already have it. But if we didn't, we could easily find it. But it just takes more time if we would where to find it again, since we already know where it is. So there's no point. We keep a set with the visited and the direction, because we have to check if it has ever been in the same position and in the same direction. Then okay, it means that there is a loop, so we can just return true. So where is that? Here. If the guard revisits the same position with the same direction, then we check it. We remove the previous obstruction because we just added it here. So here's where we add the new obstruction at a certain coordinate. And then we have to remove it after, of course, so that next time we loop through this function, we can add a new obstruction somewhere else. And one more thing we have to keep in mind is, since I don't check, okay, is the XY coordinate that we're giving it, is it already an obstruction? So right here, what I do is I check, okay, is it already an obstruction? Then there's no reason. So for example, if I get this coordinate, then it's already an obstruction. Why would I add an obstruction? What we're going to get is the exact same result as in the first part. So we are checking that. We're if it's not an obstruction, then we place the obstruction. We check the boundary, of course, and we try to see if there's a loop. If there is a loop, then we added it. Then we track it. And of course, we add to visited with direction the current state, so that we track every single position that we've been in. So once we do that, we can see, okay, that let's say this one gives us a stuck position, this one gives us a stuck position. So we add all of these to a counter, and then we return them to loop positions. And then we can just get the length of how many loop positions there are, and we print them. And this takes a second, actually, because there's just so many iterations to do. So right now we found just where the guard was facing, so it's at 43, which should be line 42, 44, because it starts at index 0, of course. So it's right here, and then if we go in the row, it should be at 37, and it looks like it's about right. So I think it takes about 20-30 seconds to run. I don't have the fastest laptop. So here we go. It ran, it gave us an answer, 1831. And if we look over here, that is the correct answer. So now let's just quickly look over the time complexity of part 1. So we have R, we have C, and we have K. So we have the rows, the columns, of course, and then K is how many cells the guard has visited during its movement. So we can't really know how many cells it's going to visit, but if it is a really, I don't know, complex, complicated graph where the guard really basically visits everywhere, then K is going to be a lot bigger, and It's going to take a lot more time to run, of course. But if there isn't that many obstacles, for example, and if the guard can just pass right through and get out, then it would be very simple to run it, and it would give us a result almost instantly. So this does matter for the time complexity. And if we think of the rows and columns in terms of n, then I wrote some time complexities in terms of n here. But here we have the reading the map, finding the guard start, simulating the movement, and the total, which is n plus k, which is pretty decent, almost O of n. And then we have the space complexity, which isn't too bad either. But then when we go to part 2, since we're iterating over every single possible position where we could add a new obstacle, and then we have to check, okay, is it a loop? And then we have to basically check a lot of times for a lot of different positions if it causes a loop. So it introduces a whole new level of complexity. So in this case, the total is n plus k squared. So it's not really n squared, which is good, but k is still quite a big number. It's how many times it traverses through the grid. It's not as big as a grid, but it's still quite complex. So that's why it took about 20 to 30 seconds for me to run it. And the space complexity is the same, so it doesn't really change. But yeah, this is a lot slower to run. And what we could do to improve is to either run it in parallel or to make slight improvements here or there, or find a slightly better algorithm instead of, okay, going step by step. We could just take this whole column and then find, okay, where the next obstacle is, and then just like sort of teleport to it. So we don't have to iterate, I don't know, 20 times. It would be a bit more efficient, but not crazy more efficient. So parallelization would probably be the most important thing if you just want to make it a bit faster. But the time complexity would still be very similar. So that was the time complexity. Now, once again, if you guys want to join the private leaderboard, I will leave the code in the comments. And there's quite a lot of people that have joined now, so that's great. And I will see you guys tomorrow. Happy holidays.